We are going to discuss about the orthogonal curvilinear coordinates, cylindrical coordinates. That is, we are going to use the results of orthogonal curvilinear coordinates and we are going to write the differential operators in cylindrical coordinates like our gradient, divergent, Laplacian and curl. Okay. Now, for that, let us consider a right circular cylinder. Okay, we are having a right circular cylinder and having z-axis as common, and we are having the concentric. We are having a concentric circles about the point O. Okay. Now we know as such we are having z as common. So the right circular circles with z as common in the xy plane. See, this is our xy plane. This is our xy plane. This is our xy plane. Okay. See, in this xy plane, we can write r is equal to root of x square plus y square, that is equal to a constant c. Okay. Now we can have half plane axis through the angle theta. So when we are considering theta, as we have already told, theta is equal to tan inverse y by x, that is also a constant, and we are having planes parallel to xy, so z is equal to constant. So these are the things we are considering for cylindrical axis. See, for that we have considered a point P in the space here, and it is having a Cartesian coordinates, say x, y, z. It is having Cartesian coordinates x, y, z, and to find the position P in the cylindrical coordinates, we have drawn the radius vector r. This from O dash. Okay. And then we have drawn the perpendicular, that is PM to the Z axis. This is a perpendicular PM to the Z axis. See, this is the Z axis and we have drawn the perpendicular. And finally, what happens? OM is parallel to OM. See, OM is parallel to O dash P. OM is parallel to O dash P. Okay. You can draw a little bit like this so that it is parallel. Okay. Okay, so let this be P and we have drawn the perpendicular here also. So now that we have to find the angle. See, now let us see. See if this is a phi. Okay, so this is phi, and then we have to know the position of the point P in this spherical. We'll draw this figure. I think this figure, our O dash P is parallel to OM. Okay. So, now we want to find the cylindrical coordinates. In order to find the cylindrical coordinates, what we have done, so we are done now this having a Cartesian coordinate x, y, z. So find the cylindrical coordinates. We have just drawn a radius vector r. Okay. So we have drawn a radius vector r from O dash. And then we have drawn this PM is parallel to the Z axis. See, now it is parallel. Our first figure, it was not parallel. So now it is parallel. PM is parallel to Z axis. And finally, OM is parallel to CO dash P. So now the angle, that is MOX. See, MOX. This is X. See, now the axis, the angle MOX, that is theta. We have marked MOX as theta. Okay. And the position P in the cylindrical coordinates is represented by R, theta and Z. We have specified the position of the point P in the cylindrical coordinates R, theta and Z. What is the R? See, R is the distance in the XY plane. R is the distance in the xy plane from the origin to the cylinder to which the point P is lying. And theta is actually angle in the xy plane. See, because here we have taken Z as the distance from xy plane to the point P. Okay, and Z is taken as a common axis. Now, we can write the transformation coordinates x, y, z and the cylindrical coordinates r, theta, phi as x is equal to r cos theta, y is equal to r sin theta, and z, as we have taken common, z is equal to z itself. See, as we have already told, we are having a right circular cylinders having z axis as common. Okay, and which forms families of concentric circles about the origin O. Okay. So we have taken r is equal to root of x square plus y square and theta is equal to tan inverse y by x. Now we want, as usual, as we have done in spherical coordinates, we are going to write for a dx, then we write for a dy, and then we write for dz, and then we write the line element in Cartesian coordinates as a ds square is equal to dx square plus dy square plus dz square. So we have written a dx is equal to dou x by dou r into dr, again dou x by dou theta. Here we are having the coordinates as r, theta and z. Okay, into d theta plus z we have taken as common. So now we are, and here we don't have z term also. So how can we write? We are having x is equal to r cos theta. When you are differentiating x with dx by dr, we will be getting cos theta dr. Then dx by d theta cos theta differential is minus sin theta. So minus r sin theta d theta, that is dx. Okay. Similarly, we can write for dy also. Dy is dy by dr into dou y by dou, I'll write dou y by dou r into dr plus into d theta. What is that? See, when you are differentiating with respect to r, you will be getting as sin theta dr. Again, sin theta is cos theta d theta. Okay. Oh, r is there. R sin cos theta d theta. And dz is equal to dz itself. Okay. Now, the line element in the Cartesian coordinate system, ds square is equal to dx square plus dy square plus dz square. This is little bit more easier than that of what we have done in the spherical polar coordinates. Now, when we are substituting, we will get it as ds square is equal to dr square. Okay, cos square theta plus sin square theta will become 1. Okay, dr square plus r square. When you are solving, you will get it as dz square. Now again we are going to compare this with our standard equation, that is ds square is equal to h1 dq1 square plus h2 dq2 square plus h3 dq3 square. So from here we are going to write what is the value for q1, q2, q3, scale factors h1, h2, h3. Okay, so what is q1 here? q1 is dq1 the whole square and dr square, and what is the value for h1? h1 is 1. So q1 equal to r and h1 is equal to 1. Again, r square d theta square and h2 square dq2 square. So what is h2 square? h2 square is equal to r square and dq square is equal to d theta square. Again, h3 dq square and dz square. So what is h1? h3 is 1 and q3 is actually z. Now see, with these values we are going to substitute it. Already we got derived the value for divergent, gradient, divergent, Laplacian and curl. So let us write the first differential operator, that is gradient. Gradient is grad phi is gradient is grad psi or del psi is equal to u1 by h1 dou psi by dou q1, u2 by h2 dou psi 2 by dou q2 and u3 by h3 dou psi by dou q3. What is u1, u2 and u3? That is r, theta and phi. What is h1, h2 and h3? 1, r and 1. And what is q1, q2, q3? r, theta and z. So, and so we can, if you don't want psi, we just write a del only. Okay, so we can finally write it as del. If you want, you can include a grad psi also. Gradient psi is equal to, including these values, we can write gradient psi is equal to, instead of u1 we are going to put it as r here, instead of u2 we are going to put it as theta, and instead of u3 we are going to put it as z here. Okay, so u r, u theta and u z. U suffix r, u suffix theta and u suffix z we are going to put. Okay, so instead of u1, ur, h1 is 1 itself. Dou psi by dou q1, q1 is r. Okay, now what is u2? u2 is u theta, h2 is r, so 1 by r, dou psi by dou theta, plus u3 is u of z, and h3 is again 1, so dou psi by dou z. So this is what is the gradient. Okay, now we shall see about the divergence. So divergence, we have written the standard formula 1 by h1 h2 h3 dou by dou q1 v1 h2 h3 dou by q2 v2 h3 h1 and by dou q3 h1 and h2 v3 is there. Sorry, v3 h1 and h3. Now we know what is h1 into h2 into h3. h1 is 1, h2 is r, and h1 is 1. So we will get it as, together we will get it as 1 by r only. Okay. Now what is dou by dou q1? q1 is r. So dou by dou r. What is a v1? V1 is vr itself. Okay. That is what is h2 into h3? That is r. Okay. Plus, if we want, we can write like this. Then what is dou q2? q2 is theta. V theta. What is h3 into h1? That is 1 itself. Plus dou by dou z. V3 is vz. What is h1 and h2? That is r. Okay. Now if we want, we can again remove, or we can write like this also. Like 1 by r. Separately each term we can write r v of r. Plus again 1 by r dou v theta by dou theta. We have just removed the bracket. Dou vz by dou z, because 1 by r and this r has gone. Okay. Now we can write for our Laplacian. Laplacian also, we are having the standard formula, that is del square psi is equal to 1 by h1 h2, again dou by dou q1, h2 h3 by h1. As I told, repeatedly I am saying, only first term you study, second term it comes to be the cyclic. h2 will become h3, then h1 by h2 plus this h3 will become, okay. Now as usual, we are having the values here for substituting. We are having the standard values for q1, q2, q3, h1, h2, h3, u1, u2 and u3. Now we are going to substitute it here. Okay, we can substitute here. So 1 by h1, h2, h3 is 1 by r again. So on substituting, we will be getting 1 by r dou by dou r into dou psi by dou r. For if you want, you can write this term together as dou square psi by dou r square. Because this r and this r will get cancelled. So you can write dou square psi by dou r square. Okay. Plus again we have substituted dou by dou theta 1 by r into dou psi by dou theta. Okay. So we are having dou square psi by dou r plus, no, we are going to take the differential of this term. Sorry, I was just telling only about the first term. R and R will not get cancelled. See, this is 1 by r, that is common for all the terms. See here, 1 by r is common for all the terms. We are going to take the differential, that is r into dou square psi by dou r square plus dou psi by dou r, and this dou r by dou r is 1 itself. So we will get here two terms. And if you remove this bracket also, you can write it as dou square psi by dou r square plus 1 by r into dou psi by dou r. Okay. Again here also we are having a dou by dou theta of 1 by r into dou psi by dou theta. That when you are getting, you will be getting as 1 by r square dou square psi by dou theta square. And here we are getting it as a dou square psi by dou z square. If you want, you can write. Similarly, we can write the curl operator also. We are having 1 by h1, h2, h3. Okay, that we are getting it as 1 by r. Then h1 u1, h2 u2, h3 u3 So h1 1 and h3 is also 1, and u1 u2 u3 we have written as ur u theta and uz, and h2 value is r. Then we are having dou by dou q1, dou by dou q2 and dou by dou q3. Here q1, q2, q3 is r theta and z. So we got dou by dou r, dou by dou theta and dou by dou z. Again v1 h1, v2 h2 and v3 h3. h1 and h3 are 1, and v1, v2 and v3 is vr, v theta and vz. So we got for cylindrical also. So this is how, using in the orthogonal curvilinear coordinates, we are getting the values in the cylindrical coordinates. Thank you.